This video is on looping, particularly the for loop. And so I'd just like to dive right into this with an example. I'm going to bring up the coin value problem that we were working on before in previous videos. Last time we changed it so that the user inputted the diameter and the mass. I'm going to change that back to functional inputs. Okay, so remember how this problem worked, or this function worked. I've got nominal coin values here, and these coins have nominal diameters and nominal masses. And so remember that I can send a measured diameter, say maybe I have a small penny, a penny that's just a little bit less than the nominal in diameter, and also a little bit less than the nominal in mass. And I send that to my function, and my function takes those values, the diameter and the mass, and returns the dollar value of that coin. So we can look at the value and we see, oh yeah, that's a 1 cent. Okay, that's a penny. And we wrote our code, and here's our code up here. Now, I'd like to show you a different way of solving this problem. At the top, right underneath the introductory comments, let me store the values of coins. So I will make a new vector. We'll call it values. Okay, and so the first value is 0.01, and the second value is 0.05, and the third value is 0.10. Fourth is 0.25. Fifth is 0.50, and the sixth is 1.00. So this corresponds to the value of a penny, then the value of a nickel, value of a dime, value of a quarter, value of a $50, and value of a dollar coin. And I will put their diameters in a table as well, or in a vector as well. So they have to they're going to correspond. So the penny was the first one I listed in the values vector, so I'm going to list the penny's nominal diameter first, 19.05, then 21.21, then 17.91, 24.26, 30.61, and finally 26.50. I'm going to brighten my screen up a little bit so I can see better. Okay, there are the diameters. 61. Looks good. And finally, the third thing I'm going to create here, the third vector I'm going to create, is a vector holding the individual masses. So I'm going to put 2.50, 5.00, 2.50, 6.25, 11.34, 8.10. There are the masses. Okay, now if I wanted to check to see if the incoming diameter was within 5% of a nominal penny's diameter, I could do like I have here. D is less than 1.05 times that, and it's greater than 0.95 times that. Or I can take the absolute value of the difference of the incoming diameter minus the diameter stored the first element stored in diameters. Okay, so here comes this D for diameter. We put a coin in our vending machine and it senses the diameter. Now we compare that to the first diameter stored in that vector. So that will be 19.05. And we're going to take the absolute value because we don't care if we're above 19.05 or we're below. Okay, we take the absolute value divided by diameters of 1, and that is now the percent error of our coin that came in versus the nominal penny diameter. And that has to be less than 0.05. Let me back up. That's not the percent error because I did not multiply by 100. That is the fractional error. So that has to be less than 0.05 to be considered a penny. And similarly, the absolute value of the mass that's coming into my function minus mass of 1 divided by mass of 1, that also should be less than 0.05. Those both need to be true. The diameter has to be within 5% of a nominal penny, and the mass must be within 5% of a nominal penny's mass to be considered a penny. So I'll put an if statement there. So if that's true, then the value I will assign, V, equals the value I will assign is values of 1. Put a semicolon there. What this is doing is everything that this did previously. We're being a little bit slick about this now, where we took all of those values we typed and instead we put them in a table right at the beginning, or a vector right at the beginning of the code. So now we're comparing that diameter and mass to values in those tables. So we can continue on like this, and we can say, let me end that. And we can say if, and I'm going to copy and paste this now. So I'm going to do Control C, Command C, and paste. And I can just change now if I want to compare it. I'll put a comment here. Compare to penny. Right? But now if I want to compare it to nickel, all I have to do is change this 1. This 1 represented the first element in the diameters vector to a 2, because now I'm moving on to, let's say, a nickel. So I just need to change this 1 to a 2. Now it looks at the second element of the diameters vector, which is the nominal size of a nickel. I need to change this to a 2 as well. And I need to look at the mass of a nickel, so I'll change that to a 2, and the mass of the nickel there. And then if it passes that test, I want the value V to be the second value in the values vector. Okay, so you can imagine now I can continue on like this. I'm not going to comment every line. You'll see why in a little bit, but I can copy and paste this. I can change this to 3. So we're going to compare that to the third coin. Then compare it to the fourth coin. Then compare it to the fifth coin. And how many coins do we have? We have 6 coins. So then there will be one more coin. So we'll compare it to the 6th coin. And so we've got that. So we're comparing each element in these vectors to our coin. So that does the dirty work for all this stuff down here. Now if you find yourself copying and pasting, and here's the key point. If you're copying and pasting and you're just changing numbers in a pattern, as we have here, we copied and pasted blocks of code and we changed a number in a pattern. Our pattern was 1, 2, 3, 4, 5, 6. If you find yourself doing that, then the code might be a good candidate for a for loop. What I can do is come up here, right after we've defined our values, diameters, and masses, and I could say for, and notice it turns blue when I type for. For is a reserved word. It means a very particular thing in MatLab. We don't want to name any variables for, and we don't want to name any functions for. It's a reserved keyword. And I'm going to type for, and I'm going to pick a variable. And we refer to this variable that's in this for statement as an iterator. And typically an iterator is I or II or J or JJ. So I'm just going to pick II as my variable. And I'm going to say for II equals 1 colon 6. Now you've seen this syntax before. Let me bring up the command window. Let me clear the command window. I think it was the second video when we were learning about the colon operator. We could set a vector. We could say v equals 1 colon 6. And lo and behold, we get numbers that start at 1, go till 6, and increment by the default. And the default was 1. And it didn't have to be this way. We could start at whatever we wanted. We could finish whatever we wanted. We could step by whatever we wanted. 1 colon 2 colon 7, for example, starts at 1, increments by 2 up to 7. So there's my vector here. So when I type something like II equals 1 to 6, I get II is this vector, 1, 2, 3, 4, 5, 6. Except when I put it in a for statement, this is a for statement. The for statement considers II one element at a time. So it will set II equal to the first element and then run some code. Then it will set II equal to the second element, run some code, and so forth. All the way to 6. It'll set II equal to 6, run some code, and then it will finish. So what code do I want to have it run? Well, remember these lines that we were copying and pasting and just changing these numbers in a pattern? Well, instead of hard coding 1 there, let me put II, and II. So now, what's going to happen is that we're going to get to this for statement, and it's going to set II equal to 1. Thus, it will compare our coin to the first element in these vectors. So a penny's value, a penny's diameter, and a penny's mass. Then when we end the for loop, it will go back up to line 11, and it will set II equal to 2. Remember, it considers everything in the vector, one element at a time. So it'll set II equal to 2 next. And thus, it'll say diameters of 2. It'll set II equal to 2. And it'll say diameters of 2, which is a nickel's diameter. Values of 2, which is a nickel's value. Mass of 2, which is a nickel's mass. And so forth, all the way up until 6. It'll set II equal to 6, and that's the length, that's the number of coins, or the length of these vectors. So the last time it goes through, it will compare our diameter and our mass and our value to the value of $1, the diameter of $1, and the mass of $1. All that I have left to do is tell MATLAB where I intend to end this looping. And I will say right there. And then I'm going to indent to make it look nice and pretty. So that, notice the 4 requires an end. Okay, when I click on 4, its end gets underlined. The 4 requires an end, and when I click on its end, the 4 gets underlined. And those are aligned spatially, right? Then, inside that, I've indented everything. Here's the if and its end, and then inside that, I've indented everything. So now I actually don't need any of this stuff here. This one for loop handles 6 iterations. It goes through this code 6 times, comparing it to the penny, the nickel, the quarter, the $half, so the dime. So I don't need any of this stuff. It does it for me. It loops back, and it changes that number according to the pattern that we set in line 11. Now the only piece remaining to this is if it fails all of those tests, we want to set the value to 0. Right? So do you remember back here in the first time we did this code, if, else if, else if, else if, else if, else if, else, the default case was 0. So if you've got some strange coin and we don't know what to do with it, we'll just say the value is 0. So what we can do is initialize the value v to be 0 before the looping begins. So now what happens is on line 11, our value that we're going to output is 0. And now we start looping. We compare it to one of the 6 coins, each coin at a time. And if it fails all of those checks, when the code ends, v will still be 0 and will output 0. However, if it passes one of those checks, then v will be whichever value passed that check. So let me save it. And let's investigate how it works. Okay, I will clear the workspace, clear the command window, and let's try it out. So I want the value, coin value, and we'll send it a, let's say a quarter that's just a little larger than a nominal quarter, 24.28 millimeters and 6.26 grams. Semicolon, enter. Okay, it did its thing. Let's check out what value it spit out. 25 cents. Pretty neat. We can investigate more what's happening in our code if we want. We can leave off semicolons to see what's happening here. So let's do this. In my code, and this is just for educational value or debugging, I'm I typed II and I left off a semicolon. That's going to echo back to me what II is each time it loops. And then at the end of the loop, the value V is going to echo back to me. Right, so I will save that, and let's call it again. Right, let's see what happened here. So I called the function, and look, it said II is 1. Okay. Well, then, if II is 1, for this iteration of the for loop, it's comparing our coin to a penny, right? II is 1, so diameters of 1, that's the diameter of a penny. Mass of 1, that's the mass of a penny. No, it fails that check. So at the end of that loop, the first iteration, V is still 0. Then it hits the end of the for loop, and it loops back up, and it sets II equal to 2. And we can see that here. Now, with II2, it's comparing the coin to a nickel, diameters of 2. Well, that's the size of a nominal nickel. Mass of 2. That's the size, or that's the mass of a nominal nickel. So it fails that check, of course. So at the end of that loop, V is still 0. Now the third loop begins. II is 3, the third iteration. And so it's comparing our coin now to a dime. Diameters of 3, that's the diameter of a nominal dime. And mass of 3, that's the mass of a nominal dime. It fails that check as well. So at the end of that loop, V is still 0 because that's what we originally set it to. Now the fourth loop begins. And so II is equal to 4, and it's comparing our coin to a nominal quarter because diameters of 4, that's the size of a nominal quarter. Mass of 4, that's the mass of a nominal quarter. And our quarter passes that check. So now it enters this if statement inside here, and it says, okay, I'm going to set V now to be values of 4, right? Because II is 4. So values of 4, 1, 2, 3, 4, that's 25 cents. So let me set V equal to 25, and now let me echo it back. And so look at in the command window, I get V is 25. Then it loops back. It says II is 5. It's not going to pass that test. So V stays at 0.25. Then it loops back. II is to 6. It's not going to pass that test. V stays at 0.25. Then the code terminates. And I get 0.25 as my answer. Beautiful. So let me go ahead and clear the command window and clear the workspace. And I will save my function there. And I would like to give you a second example. Let's write a function called myMax that inputs we'll call it myMax4, a length 4 vector and outputs the maximum value of that vector. Right. So I'll come over here and write new function called myMax4, and we'll say that the input is v, call the output mx. I'll delete the end of the function since it's unnecessary, and I'll describe it. myMax4 finds the maximum of a vector. And I will put my name, Professor, and the date, okay, 4/27/17. Alright. Let me describe to you the algorithm that we're going to code here. Let's say I have a vector of length 4, and it looks like this. Now I want to get the maximum of that vector. One way I could do it is to set or initialize my output as pi, okay, the first element, and then look at this element, the second element, and compare it to what's stored as mx. And if this is larger than what's currently stored in mx, then I'd set mx to be this. It's not, so I move on. Now I look at this element and say, well, is this larger than what's currently stored in mx? Yes, it is. So then I set this element as mx. So now mx would be 10. Then I look at this element. I say, well, is this larger than the current mx? So no, it's not. And then I'm done, and I've got the maximum as 10. That's one way of doing this. So let's do it. I'll just code up exactly what I described there. We'll say, let's let mx be v of 1. So this vector comes at me via an input, functional input, and I say, by default, I'm going to initialize the maximum as the first value. Now I'm going to look at the second value. Say if the second value is less, if the second value is greater than mx, then I want mx to be that second value. And I'll continue on this way. If v of 3 is greater than mx, then I want mx to be v of 3. And if v of 4 is greater than mx, then I want mx to be v of 4. And that's it. That should do it. So let me save that, and let's see if it works. I'll give it a vector, call it a equals pi -101, 10, 4, and we'll send myMax4. And it says, yep, maximum is 10. Alright, it works. Just like the last example, what I find myself doing here is copying and pasting blocks of code and changing one number in a predictable pattern. Here, the block of code that I've copied is that. And the predictable pattern is to change the 2 to a 3, then to a 4. In other words, incremented by 1 each time. So just like the last example, if you find yourself doing this, then that means this is an application of a for loop. So instead of doing it that way, let me type for, and the iterator ii goes from 2, 3, 4. So it starts at 2 and goes by in steps of 1 to 4. And then if v of ii is larger than mx, mx equals v of ii. End. Sorry, I missed a greater than sign there. Yep. Here we go. So again, how this works, it sets ii equal to 2 on line 7. ii is 2. This is the first iteration. ii is 2 if v of 2, which in this example is negative 101, is larger than mx, which is v of 1 from line 6. If it is, then set the maximum to be v of ii. So that first iteration takes care of this block. So I'll delete it. Hits the end of the for loop and loops back up and sets ii equal to 3, step by 1. Now it's comparing v of 3 to the current maximum. And if that's true, then we want the maximum to be v of 3. That's this block, so I don't need that anymore. I'll delete it. Then it hits the end of the for loop, comes back up, sets ii equal to 4. Says if v of 4 is greater than the maximum, then set the maximum to be v of 4. That's what this block does. So I will delete that block. And there's my code. So I will save that. Let's test it out. My max 4 of A is 10. Of course. Now, yeah, that was great, right? But why do we need to do that? Because it does the same thing as, before, without a for loop. But how useful is this code as it is right now? Not very useful. And that's because it only works for length 4 vectors. Okay, what happens if I send a length 6 or a length 2 or length 1 or length 100 or 1,000? Well, now that I've got it in a for loop, what I can do is use the length function to first determine what the length of that incoming vector is. And let's store that as len. Okay, so len in this example was 4 now. So instead of hard coding the for loop to go from 2 to 4, let's just make it a variable or soft code it to go from 2 to len. And let me save that. So does that still work? Yes, it works for that example. But now let's take a different example. Let's say we have a vector that is a random permutation of the numbers 1 through 10. Okay, there's my vector. So the maximum there is, of course, 10. Will it find it? Yep. You cannot do this without a for loop now. You can require it be a certain length and then code that many blocks. But you want to make your code flexible. And so to do that, we take the length of the vector and then we loop the length minus 1 times. Length minus 1 because we started the looping at 2. So the first iteration, ii is 2. Then the second iteration, ii is 3. So how many iterations does it make? The length minus 1. So for this vector here, the length was 10. It looped 9 times. That's because we initialized the maximum as the first value, and then we compared subsequent values in the looping. What if AA is, a random permutation of 1,000? The number is up to 1,000, so let me display it here, A. So here's A. 599, 442. It says columns 1 through 5. Then the next column is all this. So the maximum of this vector is 1,000. It's somewhere in here. It's 1,000. Let's see if my code can find it. My max of A, my max 4 of A, excuse me. My max 4 of A, yes, it's got it. 1,000. Real quickly, I want to go back now to the coin value problem. Okay, the last thing that should be of some concern to us is how efficient is our code. It's really easy when you're using loops to become inefficient, to loop more than necessary, and that slows down your code. Now in the coin value problem, I can get rid of this v, by the way, and this ii. Here's our coin value. And let's suppose I wanted to know the value of this coin here, one that has a diameter of 24.28 millimeters and one that has a mass of 6.26 grams. So in other words, that looks like a quarter to me. I want to know the value of that coin. Well, we worked through this once already, and what we saw was that we set v equal to 0, and yeah, it loops the first time and it fails the test the first time, because the first time it's comparing it to a small cent, penny. Then it loops again, and the second time it compares it to a nickel, and it fails that test. And the third time it compares it to a dime, and it fails that test. Fourth time, compares it to a quarter, and it passes that test. Do I really need to compare it now to a $50 and a dollar? Do I need to finish the looping? Coin 5 and coin 6. Do I need to loop 2 more times? No, I don't. After it passed that test, in this particular example, it passed that test, I can stop the looping. I've got my value. Okay? I have 2 options here. Number 1, if it enters this if statement, in other words, it passed the test and the value becomes the value that it should be, I can type break, B-R-E-A-K. And when I type break, you see that lights up in blue. Okay, that means that's a reserved keyword, and I don't want to make any functions called break, and I don't want to make any variables called break, because that means a specific value. That means a specific thing in MATLAB, break. What that means is, it tells MATLAB to break out of the loop that it's in. And remember, if is not a loop, for is a loop. So now what we have is on the 4th iteration, it passes this test, it sets the value as a quarter, and then it's going to break out of the for loop. And since there's nothing after the for loop, the function is done. So let me save that and demonstrate it to you. Value, 25 cents. Okay. And now let me show you that it did indeed break out of the loop. I'll put that II back. Remember, we were putting the II there to show the value of II as it looped. So I'll put II and I'll leave off the semicolon. And I will do that function call again. And what do you see? You see II was 1, II was 2, II was 3, II was 4, corresponding to the rows of this table. II1, second row, third row, fourth row, and in the 4th row it hits a match. So it terminates the looping altogether. Breaks out of that loop. Now our second option because there's nothing after the loop, we can tell the function to return the value v, which terminates the function altogether. So I'm going to type return instead of break. And you'll see again that return lights up in blue. Okay, again, that's a reserved keyword. I don't want to name any variables or functions return. But so what this does is now, it's slightly different, but in this application, it works the same. When I get a match for the quarter, it sets the value to be v and then exits the function. The break broke out of the for loop, and because that was the end of the function, it also ended the function. So let me save it. Clear the command window. And let me call our function there. And you'll see we left the II there. It loops 1, 2, 3, 4 times. Let me see what it returned. Value, 25 cents. Now our code is as efficient as it can be because it does not loop that extra 5th and 6th time. Imagine if we sent a penny, right? It only really has to loop once, the first row of the table, and then it can exit. All right, let's go over the key points. Key points. Okay. Well, for is a keyword, and when you type for, it means something very specific, and it needs an end. And the for needs a control statement. I don't know that I use that phrase. This is a control statement, such as II equals 2 to 4 or 1 to 6. That's its control statement. It doesn't have to start at 1. The iterator, II, does not need to start at 1. It does not need to end at 6. It does not need to step by 1. You can have it step by 2s if you like, 3, 4. And it does not have to be II either. You can set it to whatever variable name you like. Okay, but II is a common one. And what it does is it sets II to be, in this case, 1, and it executes whatever is in between for and end, with II being 1. Hits the end, and it comes back up, and sets II equal to the next element in that vector, which would be 2 in this case. And then it executes those lines again, and it comes back up all the way until II is 6. It executes these lines, hits the end, and then continues going if there was more code after that. So that's for. We also saw the break keyword. This breaks out of a loop. It breaks out of the current loop that you're in. Remember, if is not a loop. If was not a loop, so when we hit the break here, it broke out of the for. We also use return. When we hit return, that exits the function and it returns the current value of v. When do you want a for loop? When do you want a loop? If you find yourself copying and pasting, and changing numbers in a predictable pattern. Okay, and you can go back and you can look at these examples. Each example I did it blocks at a time, and we looked at the block, We said, oh yeah, when I go from this block to this block, all I'm doing is changing one number in a predictable pattern. So we can combine all of those blocks and put those blocks into a for loop.